we've done over at the University of Kansas, doing remote monads, or how to get your monad to work in a remote location instead of locally, and composable network stacks, which is basically a chain of natural transformations that we'll look at. So first, more familiar ground, we've got remote procedure calls. We basically have some way of serializing and representing a function that it lives on a remote location, and we serialize that with the arguments and send it across the wire to be executed. Remote in this sense is the cloud services or IoT or anything of that nature, some kind of restricted or limited resource that you want access to. And then the mechanism for serialization is usually implementation specific. For remote monads, we're looking at having monadic computation that is going to be serialized and sent to the remote location. And when we say remote in this instance, we're taking a little bit broader perspective and saying anything outside of our local runtime system. So this could be file systems, graphic cards, things of that nature that we're able to do. And we want to serialize the control in addition to the primitives, the procedures that we're sending across. And we want to be able, the biggest problem that we have with remote procedure calls is that we have that extra cost, right, of the network sending things back and getting them returned. So we want to be able to minimize that by bundling the procedures together as much as we can, so that we don't have to pay that cost. So the question that we want to answer is, how can we maximize those bundlings? So just as a quick example, we have a blank canvas library, which is looking at remote being the client's browser. So we're drawing using HTML5 canvas. And so here we've got a couple of the procedures that we want to do. We want to change the width and the style of the line that we're drawing. And so we have a monad here that we want to set the width to 20 and the color to red. Now you can imagine we kind of want both of those things to happen before we draw. Sending them one at a time is kind of tedious, and we can do better than that, right? So we want to look at having that structure, being able to bundle it together and send them over together. And we've got a run function that we see, or a send, where we're taking this canvas object and being able to interpret it into usually I/O and executing it. So here's a slide from 2 years ago. We had the remote monad design pattern, and we had a connected toaster that had a couple different capabilities. It could talk, it could toast, it could get the temperature. And here's just wanted to show that we've got 3 things here, and we were able to bundle it into 2. Depending on what you're doing, you can get a lot better than that. But we just wanted to show that we had an ad hoc way that we were able to bundle these commands. But we can do better than just the ad hoc. Is there a more principled way that we can do these things? So let's start, and we'll build a model for RPC, and we'll do terminal I/O. So we'll have a remote machine that we want to get characters or put characters to the terminal. And so we'll start with the traditional I/O. We have the get char and put char functions. And instead of just executing it right away in the I/O, we're going to separate into the structure and the interpretation. So we have our the data R that we're going to be using with some constructors to get into it, and then our run function here from R to I/O. Now this is an instance of a natural transformation where we're not doing anything to the A. We're just having it be interpreted and mapping from R into I/O. So a possible implementation of this is just using a GADT, where we are mirroring the functions that we are wanting to call. So we have get char R and put char R as our constructors, and then some smart constructors, and then our run function is just pattern matching on those constructors, and then we're calling those I/O functions that we want to do. We know how to serialize GADTs, and CAR is easy to do, right? So we've got the structure and interpretation separated out. We do this a lot in functional programming to have multiple interpretations with the same underlying data. So far, we haven't tackled the problems of transmitting the RPC as well as the bundling, but we already know how to do that. Albeit it was an ad hoc way for the bundling, but the transmitting these primitives isn't something new, right? So we can do that. So The question is, can we build a principled way of amortizing the mechanism and using stack transformers to be able to do that, since we have that run function. And it's the end of the day of Haxl and everything, so we've only got 2 slides of notation to introduce, so bear with me on that. So here's a natural transformation. So for all A, we're going to map from some functor F into a functor G. The biggest thing with these is that we're not messing with A at all. We're just taking it from one structure into another. So that means we can, in that rule at the bottom there, we can do an F map before or after the translation. It doesn't matter because we're not touching the A that's inside there. In Haxl there, we've got the. Can you see my cursor here? Nope. Okay, so we've got the tilde arrow there, and that's just going to hide the A for us and works for type checking purposes, and that's kind of what we'll be showing as a transformation from F to G there. On the right there is something, believe it or not, is called Oxford brackets. I don't know if that was the reason why our paper got accepted, but it didn't hurt, right, since we're here today. But it's saying that we have an interpreter for F that we're using G for, okay? So what we can do is take that and chain them together. So we have a natural transformation that have an interpreter for F1 in this case, and we're able to return an interpreter for F2. So if you give me a way of interpreting F1 in, let's say, the IO monad, then I know how to handle F2, and I can put it in a way of making it an F1 or a set of F1s, and I can further interpret that. So with the basis of that F1 interpreter, I can make an interpreter for F2. And we've got the chain there showing that F2 depends on the interpreter of F1. And so we're able to chain those through. And then the outside G is often omitted, but it's usually IO in the cases that we've seen. So what we can then have is a full network stack of these things. So on the left we have the local side, and on the right is the remote. So we have we can start with some functors at the top, and then have it translate into an intermediate representation, and then something that we're able to serialize. And then we have the dotted arrow there to show the network transmission. And then on the remote side, especially if it's a Haxl to Haxl setup, we're going to want to decode into those structures, pull it out, and then use our interpreter for the primitives that we have set up. In the cases that it's not Haxl to Haxl, then we don't necessarily have that mirroring, but it is helpful when it is the Haxl to Haxl. A particular instance, if you think of JSON RPC, it's got a setup protocol, and so it can be implemented in any language, and so we would have that serialization step be into those JSON objects. All right, so let's jump back with our R. So we have this new diagram here, the network stack, where we're going to be taking R to bits, send it across the wire, and then decode it and execute. So we'll just introduce the send API, which is just a wrapper around the byte string, and we'll be able to see how each of these steps work. So first we'll encode, and if you look at the type there, we have send API, and then the tilde arrow to IO. So we have this function where the first argument is, I know how to send this across to the remote location. And with that, we can say, you give me an R, and now I can send that on the remote location to be executed. And the implementation there, we're just going to be pattern matching on the constructor, putting it to a byte string, and then and having the send API wrap around that. And then we're able to call that function, which will give us the way of transmitting it and getting the result back, and then we'll read that result back. For this example, we'll just have a trivial model of the transmission, but we've got the send API IO to send API IO, which is basically if you give me a remote interpretation of this byte string, then we'll end up with a local one. And then decode R, we're taking it from the byte string back into R. So we see that we have the get char r. We were just using the show instance before. So we were able to just pull that into R with the get char r, and then call our function there that was given as the input parameter, which is our R to IO. And then to tie it all together, we bring back our run function, which was the IO implementation of just the get char and put char. And we're able to chain these all together. So encode R, transmit, send API, decode R, and run. So we now have a way of getting from R to IO in the remote location. So what are some of the things that we want from a remote monad? We can follow the monad transformer lift laws, which basically say if we're sending a return, well, we don't need to go all the way to the remote location to get that result. We already know that statically, so we can just return it right away. And then for a bind, when we're sending two things, it's the same as if we were sending them one at a time. This gives us freedom to be able to do different bundling strategies. And so a send is a natural transformation from the remote effect to the local effect. Okay, so we still haven't done anything with monads yet, so we'll have to do that. So now we can have a monad that's parameterized on our primitives, the things that we want to send. And so we parameterize this on R. And you could use a bunch of different ways. We could use the monad stack transformers or a free monad or other things. We decided just to do the most direct implementation of having the bind return constructors to have it be an instance of monad. And then we are able to go from the monad and then using the rest of the stack, take it into R and then to be executed in the remote location. But that only lets us do one at a time, right? And the main part of this talk is being able to bundle those together and amortize it. So to make sure that we can get things working, let's do a trivial packet where there's just one item in a packet, and we'll go from there. So our packet's also parameterized on R. And now we have, we'll need a natural transformation of something that knows how to handle a packet, and then we'll be able to handle the entire monad. So we'll be able to go from monad to the packets, serialize it, and send it on to the other to be executed. So then the question is, well, what's the best way to do this? Doing it one at a time, this is what we were calling the weak remote monad, where everything's just getting sent one at a time. So what's a better mechanism, or what's a better packet that we can use for this? A couple years ago, we observed that the remote procedures, that there is kind of two types that we might have. Those that we want the remote effect, but don't have any result coming back. An example like we saw earlier, when we're setting the width of the line or the color, there's no meaning result. It's just results that are in unit. And then there's procedures where we want the remote effect as well as the result to come back. And with that, we were able to say that we could chain any number of commands and punctuate it with a procedure. So in the toaster example, having it say something, there wasn't a result back. It was just like a put string. So you could say 100 things and then get the temperature, and that would all be in the same packet, though it would be a pretty annoying toaster. So is there a better packet than this? This is the implementation that we had for the strong remote monad a couple years ago, having that structure. Looking at monads, we found that monads don't make packets very well. And the reason is because bind is a hard thing to serialize. So here in this code, we've got an is point and path, which is just one of the Canvas things where is this point inside a drawn path? And depending on that answer, they're going to do one of two things. And so we don't know what to send with line width at this point. So we can't bundle these two operations together. So bind gets a little bit tricky that way. But applicatives are something that work really nicely for us. So the nature of applicative is that the different parts of the operation, or the different arguments, they're not going to interact or depend on each other. So we're able to send those to the remote location together, and then combine them again locally. Using applicative do on the right there, we're able to have the familiar do notation that we see with monads as well, and have it be in applicatives where we'd like it. This was also proposed by Jeremy Gibbons in his free delivery paper, and that was what he was talking about was just because monads are hard, just don't use them. Use applicative functors instead, and you don't have to worry about bind or some of the other constructs that monads have. And then Haxl internally is able to use applicative functors to combine some of their things, and we'll talk about that in a little bit as well. And kind of hindsight's 2020, we proposed that sending applicatives that you can use an applicative packet as well. So this is kind of the cross of remote monads and remote applicative functors with the different packet types. So 1, 2, 4, and 6, we were able to investigate and see kind of what those things were. 1 and 4 just being the one primitive at a time, nothing interesting or surprising there. And then the 4 and 6 were, then 2 and 6 were kind of the stronger variants that we were going to be able to do a little bit better. But let's take a look at that 3 of getting the remote monad to use the applicative packet to get better bundling than just the commands and punctuated by a single procedure. So in order to do that, we have to figure out how we can get a monad into an applicative. But we can't get rid of those binds, right? So what we can do is have this kind of chain of binds that are, and have as big of an applicative functor as we can that's connected by these binds. So there's a couple different tricks that we can use to minimize the number of binds that will allow us to have better packets to continue on to the remote side. So here's a couple of the tricks. So the first is to do the obvious things. Return map straight to pure. And then the sequencer arrow goes straight to the star arrow of the applicative functor. So those ones are the easy ones. So whenever we have kind of the sequence, in our examples, put char r, if we had those just in sequence, that would be able to turn into a applicative functor where we're ignoring the result of what's before. The second trick is taking a bind or a command that's bound to something that we know the result's going to be unit. So that's the same as if we did a star arrow, and that's something that we were able to see in the previous work. And then the other thing is kind of what Haxl is doing. So what they found out and are using is that if we have this kind of structure, that Q1 and Q3 are ready to go. They're ready to be sent across. They're not depending on anything. But Q2 and Q4 are blocked. They're waiting for the left side of the bind. If you have primitives or procedures that are read-only queries, then you can have reordering because they don't affect each other. So they're able to send Q1 and Q3 together and then get the result back and then send the result to Q2 and Q4 so that they know what to send and then send those on. So this only works if you have read-only queries. Then they're able to do this reordering and get a little bit more juice out of it. So in writing the remote monads, what we've got to do is write the monad, transmit the applicative. And that depends on what the classes of primitives that we have. Do you have primitives that are going to be effectful on the remote side? Or is it going to be read-only queries? So we're able to subdivide those primitives into the commands or the procedures, what we call those. And then the read-only, the read-only only works if you have all of the primitives are read-only. So kind of looked at what would happen if we had a mixture of those two things, and it wasn't looking very pretty. And there might be other classes of primitives that we haven't discovered at this point. So that's something that we're trying to keep an eye out on and see if there are things that we can do to do better with that. And all of it is trying to get the biggest applicative chunks out of the monad and be able to lower that network cost. So some of the use cases that we've done, a lot more details in the papers about these. We've got the remote JSON, which is a JSON RPC implementation, which mapped really nicely with our original command and procedure setup, where notifications are commands, and then methods are the procedures. And in the JSON RPC protocol, they actually have set up for the batching of requests or bundling. And so with our layer that's on top of remote monad, you're able to select if you would like the bundling of applicative or weak or what you want. And the reason for that is with the JSON RPC spec is if you're batching the procedures together, then the server has the option of doing them in parallel. So if the order does matter to you, then you probably don't want that, and so you'd be doing the weak version of that. All right, and then the remote binary was kind of in response to, well, remote JSON is good and all, but you're passing strings across, and can we have a little bit better setup that way? So that one's using the applicative bundling, and then we're encoding to byte string and sending that. That one we looked at experimenting with exceptions as well, which is one of our future work items, where is the exceptions going to happen for this Haxl code? Is it going to be handled locally or on the remote side, and how do you handle that? So that was something that was a little bit unique with this one, of figuring out, well, if an error happens, well, the way that we handled it, I guess, is on the server side, we just wrapped all the interpreter code in a try, and then if that was going to give us an error, then we'd have an error bit at the front that we would send back, and then we'd have a check for it and reproduce the exception on the local side. Another way of handling it was having an alternative packet, which mimicked the applicative packet, but had another construct where you're able to send two procedures over, or two of whatever, and it's a do this one unless it fails, and then you can run the other one. And then Haskino is something that Mark's been working on, where your monads are encoded to binary streams onto an Arduino board. So he's able to have a shallow embedding of Haskell running on a tethered Arduino, or doing a deep embedding onto the Arduino and running non-tethered. And then we've got blank canvas, which we've talked about. We're doing actual HTML5 code. So the serialization step can be whatever you want it to be. And so it's real nice to have this transformer stack, because you can insert whatever steps you want inside there. And then we had what we call a toy Haxl example that was using the applicative bundling and having the read-only primitives to show that we could handle the reordering of the primitives. We didn't handle the caching or some of the exceptions and things of that nature. So that's why we call it the toy Haxl example, but just showing that how general our framework was. And so in conclusion, we see that remote monad's a pretty useful thing, or at least we think it is, and that we're able to have a send function to run something remotely. So you can take a monad that isn't set up for bundling and things of that nature, pull out the primitives, and then we're able to have a remote monad. And some of the open questions that we have is if we can generalize more of the classical monads. So what would a remote state monad look like? Kind of thinking of a state monad where the state isn't really serializable. It can only remain on the remote side. How do you handle that? What does that look like? So that was kind of the other things that we were looking at. But that's all I have. Is there any questions? You're welcome.
I'll just speak up. Thank you. That was a nice talk. At one point you said, oh, very different. Monads necessarily are serialized, where applicatives are not. I didn't understand why you were having trouble.
Well, so it's with the bind. So when we've got the bind, we have a function that needs to be applied with the result of a previous remote operation. And so we would have to do some static stuff with the keyword like we saw earlier, or other things to be able to take a closure and send it over to a remote side.
The difficulty is transmitting a function.
Yes. Yes.
It's not bind per se, but there's a function.
Right, yeah, because we're binding to a function. So yeah, to be more precise, the function sending it across, yes.
Right, so one way of formulating applicatives, they also have functions in them. This is the point here. Carefully using a formulation of applicatives where there's no function.
Right, yes. And the applicative too, we're doing the combination things locally. So the arguments are getting sent over, and then they come back, and then we apply the function to it. When we have like the dollar arrow, or the arrow dollar being applied to multiple things, if that makes sense.
Well, I understand that the key issue is that transmitting functions is not. I believe that.
Okay.
But then you say, okay, but we can turn a monad into applicatives to transmit it. I didn't understand how you were doing that.
Yeah, and so what I'm talking about there is just getting the most applicative pieces that we can out of it, and then we're separating that by bind. So as much as we can of the primitives and making those into the applicative parts of it, we do that, and then we send that off, get the result back, and then apply that to the function through the bind, and continue on.
Okay.
Yep.
Thank you.
Yeah, so I have two questions, if that's all right.
Sure.
The first one is, I might be confused, so sorry if I'm misunderstanding, because it's quite late today. So you said you had like a natural transformation from your R to IO.
Yes.
Yeah. But R wasn't a function, was it?
So yes, we did a little bit of hand waving, but we feel that it could be a trivial, just adding another construction that R would be an FMAP, or an FMAP constructor that we could then have a full instance of functor.
And then it stops being serialized, isn't it?
It all works out.
Okay. I'll have a look at the paper, I guess. Yeah. The other thing is, I've been thinking about serializing sort of monadic code, but for a different application. So if you imagine like you have a script in a computer game, something like that. Like when I say a script, I don't mean like dialogue, like one character does this, another character does that. You might have. I was thinking it would be nice if you did have a monad you just wrote the script in. But you need to be able to save the state in the middle of the script. That's kind of where I was coming up with what was serializing a monad. I don't know if you had any thoughts on that particular idea.
Well, so you could have a monad stack in there as well. So you can throw the state monad on top, and then as we go through, you're able to check the state and send things over and get it back and do things of that. So yeah, I think that would be just fine.
Okay, I'll think about it.
I can just add. You mentioned you were reordering things to maximize applicative usage. That's sort of the purpose behind the applicative view extension, right? Is that it tries to be clever about that. So is there interaction, and do you make use of applicative view to get this, or can you not do that for some reason?
No, so the applicative do works fine with everything. The reordering was more when we had those binds and things set up. So what we had initially is you're just stepping through left to right. Oh, we found a bind. Send everything that you queued up and get the result back. But what Haxl has found that you go through everything, find out what's not blocked, put that into a bundle, send it off, get the result back as maybe a tuple, a for tuple, whatever you ended up with, and then you can apply that to the right side of the binds, to the functions there.
So it's additional optimizations on top of AUL.
Exactly. Yeah, and only for read-only queries that aren't going to mess with each other for that.
Thanks so much for very interesting. At one point, you touched on exceptions, and that triggers the thought in my mind, which where the network suddenly connects to pages, there pretty much in the middle, and the pair that you covered was the easy one. Networks have all kinds of interesting failures. We haven't talked about how to deal with those.
Yeah, so that's the future work is figuring out what those failures mean and if we're going to have the server do that for, depending on the errors, of course, or which ones we can handle locally on that. So yeah, that's definitely something we're wanting to look at.
One last question.
Really, perhaps you know consideration. Now, Haskell library has grown significantly applications that might change the remote handling.
Yeah, and we've started to look at that as well, of figuring out if that is and have a remote static or something where instead of separating the primitives into this GADT structure and interpreting that, we're able to just send the functions across using the static keyword. And so yeah, we have started looking at that, but it'll be nice seeing the previous talk and how they did it to learn a little more. Thank you.